Hello everybody, welcome back to Physics 331. So today what I want to do is I want to continue our discussion of lock-in detection. What we saw last time is that our lock-in detector takes two inputs, a reference input and a signal input, and multiplies those two signals together, does some filtering so that only the low frequency component of those multiplied signals survives, and then averages. And what we found is that that average signal depended on the difference in frequencies between the signal input and the reference input. So that was omega s minus omega r. And after doing that averaging, because this function is sinusoidal, it only survives to a non-zero value when omega s and omega r are exactly equal. And that was kind of the essence of lock-in detection. What I want to start with today is to ask the question, suppose that our signal frequency and our reference signal frequency are close but not exactly equal. So how well does the average of this V out prime, remember the notation V out was the product of the reference input and the signal input. The prime means that we've done some filtering so that only the low frequency terms survive. And then the angle brackets is our time average. So how well does this quantity discriminate between frequencies that are perhaps close to omega r but not exactly equal to it? Okay, so to answer that question, just let's recall what this time average actually looks like. So the V out prime was proportional to the cosine of the signal frequency minus the reference frequency. There was some phase factors, but for the purposes of this argument, they're not important, so I'm just going to omit them. So that was V out prime is proportional to this quantity. There was also some amplitude prefactors that I've omitted. And then what a time average means is that we're going to integrate this over a long time where t is our averaging time. So this is going to be our averaging time. And then to make that an average, we divide by 1 over t. Okay, but the cosine is a simple function. We could just evaluate this integral, and what we'll get is the 1 over t from out front. When we integrate the cos, we get a sine function, but we also pick up a factor of 1 over omega s minus omega r. And then we have our sine function, omega s minus omega r. And we have to evaluate between our integration limits 0 to capital T, the averaging time. And so this becomes 1 over omega s minus omega r times the averaging time times the sine of all of that stuff, omega s minus omega r times the averaging time. And so you might recognize this function. This is the sinc function. So the sinc function is defined as sine of whatever, in our case it's omega s omega r minus omega r times t, divided by that same stuff, the argument of the sine function. So omega s minus omega r times t, and so that's the definition of the so-called sinc function. Oh. Sorry. Sinc of omega s minus omega r times t. Okay, so we could plot this function. We'll plot it like this. So we'll have an axis. The horizontal axis is going to be omega s minus omega r times t. And then the vertical axis will be the sinc function. It's not maybe immediately clear what happens when omega s minus omega r times t is equal to 0, because then we have the sine of 0 over 0. But then what you could do is use L'Hopital's rule to find out what happens at that limit, and it turns out that it becomes a 1. And that's because when you take this derivative of the sine you get the cosine, and cosine of 0 is 1. And when you take the derivative of the denominator, you just get the 1. So that ratio is 1. And then if you were to plot this, because of the sine function in the numerator, this is going to be an oscillating function, but those oscillations are going to die out as omega s minus omega r times t gets large, because we're dividing by that. And so we get these oscillations that get weaker and weaker in amplitude. Okay, so already we can get some insight from this plot, right? We're trying to figure out how well does the lock-in detector discriminate between frequencies not equal to omega r. And so what we can see is that this average signal is the largest when, of course, omega s and omega r are exactly equal. And then as we go away from that condition, either above or below, the size of the output from the lock-in detector decreases. And so what we could do is we could try to characterize roughly the range of frequencies that are accepted by the lock-in detector by finding this width, the width between the zeros, or perhaps maybe better would be the width between 1, 0 and the vertical axis. So perhaps this width. And that width defines approximately what frequencies are detected as being significant by the lock-in detector. Okay, so in order to characterize the width of this V out prime average, we're going to find the value of omega s minus omega r times the averaging time that produces the first 0 of the sinc function. That's not hard to do because the sinc function has a sign in the numerator, and the sign vanishes when the argument of the sine function is equal to pi. And so what we have to do is we have to find omega s minus omega r times t. We have to set that equal to pi, and that defines where the first 0 is. And so therefore, if we isolate for t the averaging time, we get t is equal to pi over omega s minus omega r, which is pi over 2 pi, say, fs fr. And so t, this averaging time, is related to the range of frequencies by 1 over 2 delta f. And in fact, the range of frequencies is, so right now what we're calling this is our range of frequencies, and so twice that is the full range of the values. Okay, so if we want to make delta f small so that we accept only signals that are very close in frequency to the reference signal, then we have to average for a long time. And so intuitively that makes sense. So to maintain a small delta f, i.e. if we want to accept signals that are only very close to the reference frequency, we must average for a long time, and that time is set by T, capital T. So when you use a lock-in detector, one of the settings that it has is they call it a time constant. And so essentially that's how long do you want to average for. And if you want to have a very high sensitivity to only frequencies very close to the reference frequency, then you want to set that time constant or the averaging time to be a large number. Okay, good. So I want to do one other thing in our discussion of lock-in detectors. The example we started with in the last video was an RC circuit. It turned out to be a high-pass filter. And there we drove our circuit, our filter, with a pure sine wave. And of course that led to an output that was a pure sine wave. And then we could do our lock-in detection quite easily. But it's not always the case that an experiment naturally lends itself to being driven by just a pure sine wave with a sinusoidal response. And so I want to consider a situation where that is not the case, where it's not a sine wave driving our experiment. But then we could think of a way to kind of modify the experimental setup or the apparatus in a way where we could implement lock-in detection so that we could make some very sensitive measurements to measure small signals. And so the topic is lock-in detection, and specifically we're going to use it to measure the first derivative of a system's response. And this will be more of a intuitive discussion, right? Try to get a feeling for the essence of how this works rather than a quantitative kind of derivation type thing. So we'll start by recapping what we saw last time. Last time we saw that lock-in detectors can measure very small AC signals when the frequency of the desired signal is known. In our example of an RC circuit, what we did is we supplied a sinusoidal input. In our case it was an AC voltage, and detected a sinusoidal output. In our case it was the voltage across the resistor. As you can imagine, not all experiments can be driven by a pure sine wave, or at least it's not always the case that it's most convenient to drive an apparatus with a pure sine wave. And so we're going to do this by thinking of a specific example. The example we're going to think of is an ESR experiment. So consider, for example, electron spin resonance. So ESR. Sometimes this is called electron paramagnetic resonance, EPR. It's the same thing. So ESR is used to study materials that have unpaired electrons. For the purposes of this discussion, the unpaired electrons are going to act almost essentially like free electrons. And so if you have one of these ESR samples or a paramagnetic sample, it has a certain number of moles of unpaired or free electrons. And so it's like a system of free electrons that we can study. Okay, so these unpaired electrons have a spin 1/2. So we're going to consider a system of spin 1/2 electrons with the spin angular momentum along the z direction. We're going to be applying an external magnetic field, and we're going to apply that field along the z direction. And the angular momentum of this electron spins along this z-axis is going to be quantized. So electrons with the spin angular momentum quantized along the z direction. And so the quantum numbers are ms is equal to plus minus 1/2. Okay, so in an external magnetic field, applied along the z direction, the energy levels of the two states, ms is equal to minus 1/2 and plus 1/2, split. And they split according to the following. One of these states, the plus 1/2 state, corresponds to the spin angular momentum aligned parallel to the magnetic field, and the spin minus 1/2 is anti-parallel to the magnetic field, and those two states have different energies. They're degenerate when the magnetic field is 0, but they're non-degenerate when the magnetic field is non-zero. And so this energy splitting is given by E is ms, the angular momentum, spin angular momentum along the z direction, times what's called the Landé G factor. It has a value of about 2 for free electrons. It's 2.0023 for free electrons. And then there is another constant. This is the Bohr magneton. And then times B, which is the magnetic field. So the idea of a ESR experiment is to get one of these samples that has unpaired electrons, put it in a magnetic field to split the energy levels of the two spin states, and then irradiate the sample with photons. And if you match the photon energy to the splitting of the two states, then the sample will absorb some of the incident energy. And so as a picture, we could draw the energy of these two levels as a function of the strength of the external magnetic field. So at 0 magnetic field, those states are degenerate, they have the same energy, but then they split, and the splitting gets larger and larger as B gets larger and larger. And this is the plus 1/2 state, and this is the minus 1/2 state. And so what you want to do is pick a value for the external magnetic field. Maybe we call it B0 just for argument's sake. And then we're going to irradiate the sample with photons. The energy of these photons is going to be h times nu, the frequency. And if we set that frequency correct so that it equals this energy splitting at the value of B0, then the sample will absorb some of those photons and we'll measure some absorption. Okay, so in words, if the external field is set to be B equals B naught, in a typical ESR experiment, this might be, on the order of a few Tesla. Then the sample is irradiated with electromagnetic waves or photons with an energy h times nu. So nu is the frequency of the radiation, and so again, for a typical ESR experiment, this might be around, 10 gigahertz or so. So we're going to match that frequency to the splitting of the spin states. So then let's fix some of this language here. So if the external field is set to B0, then a sample irradiated with electromagnetic waves or photons with an energy matched to the splitting of the spin states will absorb some of the incident energy. Okay, just for reference, this splitting of these two states, it's called the Zeeman splitting, or it's called the Zeeman effect. Okay, so in practice, in an ESR experiment, a sample is irradiated with photons of a fixed frequency, and the absorption by the sample is measured as a function of the applied magnetic field strength. As a function of the applied magnetic field strength. Okay, good. So in a picture, what you might do is you might sweep the magnetic field and you measure the power absorption of the sample. And there's always going to be some kind of, it's going to be a narrow absorption peak, but it'll have some finite width. So if we zoom in to the peak, we'll see a narrow, sharp peak. And, this peak maybe occurs at some particular field, which we can call B0. Okay. And so that peak occurs at a field that is set, that's determined by, first of all, the frequency of the light that you're using and a bunch of other constants. All right, so that's kind of like a 5-minute description of an ESR experiment. It had so far we haven't applied lock-in detection at all. So the challenge that we have is that the absorption peak can be very weak and difficult to measure precisely. So what we'd like to do is we'd like to take advantage of the sensitivity of lock-in detection, and so we're just going to make a slight modification to how we do the experiment. So we'd like to use lock-in detection, which is a very sensitive technique. And to do that, what we need to do is introduce a sinusoidal signal to the measurement. We need to introduce this so that we have a reference signal to supply to the lock-in detector of a known AC frequency, and then we can measure very small signals of the system's response at that frequency. And so to do that, the idea is to add a small AC field on top of the average value. So we're already applying a large DC magnetic field. What we're going to do is we're going to add like a small sine wave on top of that. And so B is going to be equal to some average value, the DC component, plus some oscillation on top of that. So if we were to plot as a function of time what the magnetic field looked like, it would have an average value of, say, B average. And what we're going to do is we're going to put like a very small AC component on top of that. And so the peak to peak range of that AC oscillation is 2 times the amplitude B1. All right. So what will happen is if we oscillate the magnetic field, there'll also be a small oscillation of the observed absorption, and that's what we're going to try to look for using the lock-in detection. So doing this, one then introduces a oscillating component to the observed absorption by the sample, and we can detect this. That can be detected easily by a lock-in detector. Okay, so let's kind of imagine how this might look. So I'm going to make a plot here of the absorption as a function of magnetic field. And so we know that this is some kind of absorption peak like this. So the first step is to pick a value for B average. So pick a B average value. And so I'm going to use a value right around here to start. Okay, so select the amplitude of your oscillation to be much less than this B average value. And so I'm going to exaggerate it here so that we can draw a good picture, but we might make our oscillations so that the magnetic field has extreme values of B average plus B1 and B average minus B1. And what's going to happen is we're going to oscillate that field. So we're changing the value of the net magnetic field. And of course, as you do that, you sample different parts of the absorption curve. And so the range of values on the absorption is determined by the range of values of the magnetic field. So in this case, when we have a small value of the magnetic field, B average minus B1, we end up with a small value of the absorption. And then when we have a large value of the magnetic field, B average plus B1, we have a large value of the absorption. Whoops, sorry, that occurs at a slightly different time, so let me say like so. And so we would get this kind of oscillation in the absorption. And you can see actually in this case, the input and output oscillations are in phase. So what I mean by input oscillations is the oscillations we introduce to the magnetic field. So when this is a minimum, the absorption, which is the output oscillation, is a minimum. When the magnetic field is a maximum, the absorption is a maximum. So those oscillations are in phase. The other thing we can notice here is that for the value of B average that I picked, where the curve of the absorption is steep, we got large output oscillations. So when B average is set to a value where the absorption is steep, we get large output oscillations. So in other words, our lock-in detector is going to detect a large signal. Okay, so that's fine. Let's imagine what happens if we pick a different value for B average, a different point on this absorption curve. So we'll redraw the absorption here. Ooh, maybe I can do better. Okay, so this time maybe we'll pick a value of B average that sits at the peak. And so this is going to be B average plus B1, and this is going to be B average minus B1. And so again, we'll allow the magnetic field to oscillate. And when we do that, so when we have a minimum of the magnetic field, we would get this value of absorption. And then when we have a maximum, we would get this value of the absorption. And what we find here is that when we sit at the peak, when B average is set to be the peak of our absorption, the oscillations at the output are very small. So when B average is set to the peak of the absorption curve, the output oscillations are small. Okay, so that means the lock-in detector detects a very small, weak signal. Let's let's think about one more case and then we'll try to summarize what we found here. So here's our absorption peak. I'm going to pick a value of B average where the absorption is steep, has a steep slope, but I'll go to the right of the peak this time. And so here is B average minus B1, and here's B average plus B1. And here are our oscillations. When the magnetic field is a minimum, our absorption is large. And when the magnetic field is a maximum, our absorption is small. Okay, so that means we start at a large absorption and go to small one. And we get these large, again, large oscillations because we have a steep part of the absorption curve. But now the oscillations are out of phase, so we again get large output oscillations when the absorption peak is steep. Now the slope of the absorption is negative, and our input and output oscillations are out of phase, i.e., when the magnetic field is small, the absorption is large. When the magnetic field is large, the absorption is small. Okay, so we can summarize all of these things, I think, in one nice plot. So I'll make two plots, in fact. We'll have the absorption signal as a function of magnetic field, and then below it I'm going to plot as a function of field again the lock-in detector signal. Okay, so a couple things we saw. Ooh, sorry, before I start, I need to shift my axis here. I'm going to put this magnetic field axis in the bottom plot in the center. So we started here where the absorption curve was steep, and we found in-phase oscillations that were large in amplitude. And then we went over here where the absorption curve peaks, and we found very small amplitude oscillations. And then we went over here to where the curve is steep again but has the opposite slope. We again get large oscillations, but they're out of phase with the input and output oscillations are out of phase. So I'm going to call that a negative signal. We didn't do it, but if we would have went here, we would have found that because the slope is very shallow, we would have got small output oscillations, but they would have been in phase, so maybe it looks something like this. And had we done an analysis here, we would again saw small amplitude oscillations that would have been out of phase with the input oscillations. And if we connect all those dots, what we would find is a lock-in signal that looks something like this. And that's exactly the first derivative of the absorption peak with respect to the magnetic field. And so the lock-in detector measures the derivative of the absorption peak with respect to magnetic field. Okay, and so if you wanted to, you could then recover the actual absorption peak by integrating the lock-in detector signal. So calculating this area underneath the curve. And so you'd start with a bunch of positive area first, so that would take you to the peak, and then you'd start adding in negative area that would take you back down to 0. So that's kind of the two ways to use lock-in detection. Both are used widely. The first is to drive your experiment with a pure sine wave and measure a direct sinusoidal output. The other is to take one of your system parameters, which is not sinusoidal typically, and to add a small sinusoidal component onto it so that you can introduce an oscillating component to your output, which is going to be proportional to the derivative of the system's response. Okay, good. Thank you very much, and we'll look forward to the next video.